Okay, so intermediate value theorem. We can probably make this pretty quick. It's one theorem. It's an existence theorem. This will set the stage for a bunch of other ones we're going to do just like this. So the intermediate value theorem. This is the picture. If you get the picture, you get the theorem. So just watch how we do the picture here. Here's what it says. Here's the if part, right? There's always an if part and a then part. It's conditional statements. So if we meet certain criteria, then the existence theorem guarantees the existence of something that might be useful. Okay? So if f is continuous, we have some function f that's continuous on the closed interval from a to b. What does that mean in terms of this picture? If f is continuous on the closed interval from a to b. Now look at the xy plane here. This is the x-coordinate of that point is a, and the x-coordinate of that point is b. So what's that mean? If the function's continuous from a to b, what can I do when I'm graphing it? Yeah, I can graph without picking up my finger off the board, right? Okay. So if it's continuous on the closed interval from a to b, and if f of a is not equal to f of b, well, it's not, right? Look on this axis. On the y-axis, there's f of a, and there is f of b, and they're different values. They're not equal, right? Then what the intermediate value theorem says is that if k is any number between f of a and f of b, so between those values, those y values, so let's arbitrarily just pick this to be k. So there's the horizontal line, y equals k. What do you suppose the existence theorem is going to guarantee then? Yeah, it's going to essentially guarantee that the function f has to cross k at least once inside that interval between a and b. Doesn't that make sense? Right? If I can't draw the function from a to b without picking my pen off the board, if it's a function so it doesn't violate the vertical line test, then there's no way that I could possibly connect these dots without crossing through that horizontal line at least once, maybe multiple times, right? Everybody see that? And so what it really says then is if k is some value between f of a and f of b, then there exists not a number, at least one number. I should say that. At least one number in the interior interval, so between the endpoints, such that f of c equals k. Well, here we ended up with three of them, right? We could say that this point right here, we could call this, there's one intersection. So we could call that C1. Here's another one, C2. And here's another one, C3. But we know we have to get at least one value of C. That's all it says. Does it help us find it? No, you got to do algebra to find it. But it tells you that it has to be there, right? So here's another, like here it is in the OpenStax book, just an online textbook. It says essentially the same thing. The people use slightly different language sometimes. No, looks the same, right? There's the picture they drew. Okay, between a and b, if this function's continuous, then there's at least one value of c where we pass through that line, y equals k. Here it is in our textbook. What do they say in our textbook? So they use the number n instead of the number k. Big deal. Doesn't make any difference. But we're going to find at least one value of c on our interior interval where the function has that value. Okay, so you can apply things like this to statements or situations that don't seem very mathematical. Like we should be able to prove this statement. So we're going to take a little look at formal proof here. Right? We don't do very much of that in calculus, just because in high school, I don't want to take the time. I mean, we want to just cover the analysis part of it, and in college, you'll maybe see more proof in your calculus classes. Maybe, maybe not. To get a better idea of this result, suppose we climb a mountain starting at an elevation of 2,000 meters, okay? And ending at an elevation of 5,000 meters. So could you prove that no matter how many ups and downs you take, at some time your altitude must be 3,765.6 meters? How? How can you prove that? Because you can. Ideas. Well, let's go back and review. So there's the picture we're looking at, right? It makes logical sense, but we got to prove it. So let's go back and look at that intermediate value theorem again. And again, what did it say? If f is some continuous function on the closed interval from a to b, so we would have to show, in order to prove that statement about climbing that mountain, we'd have to define some function that's continuous on the domain that we're interested in, right? Some closed interval. And we've got some intermediate value k that's between f of a and f of b. If we have that stuff, then we can guarantee that there is some intermediate value where we pass through y equals k. We have to be able to meet those criteria, though. We have to be able to confidently make those statements about the mountain climbing situation in order to prove it. It seems like it ought to be true, and your intuition might tell you so, but that doesn't constitute a proof. So what could the function be? Like, what is it representing? What's the function here? Well, we have to have some function, right? You're climbing some mountain starting at an elevation of 2,000 meters and ending at an elevation of 5,000 meters. So we need to be able to translate this into some graph, right? I need to know what goes on the x-axis and what goes on the y-axis. There's a couple different ways you probably could do this. But what do you think? Again, look back. Look back at this picture. So the outputs of the function were f of a and f of b, and we knew that if we had some continuous function on the closed interval from x equals a to x equals b, and there were some value k which is between the output of the function at a and the output of the function at b, then by IVT, we know there has to be at least one interior value of x where the function has that intermediate value k. So what do you think?
Is it 2,000 after 2,000?
Oh, say it again. Okay, so on our graph, that would need to be 2,000 and 5,000 probably, right? Make sense? Okay, now we're getting somewhere. So on our graph, this is going to be 2,000 meters, and this is going to be 5,000 meters. And that interior, what was, I mean, gosh, it was like some crazy number. What was it? 3765.6. Okay, so there's that, right? So that's the output, but so I guess we're measuring the output of this function is going to be, we're going to say altitude in meters, right? What's the independent variable?
So wouldn't that be the f of? Because
It is, you're right. Yeah, that's f of.
it'd also be 2,000 and 5,000 on the bottom?
No, because the output is 2,000. The input is 5,000. This is the part that's a little tricky. There's different ways to do this. You could come up with some different inputs, but the output for some value of your input, whatever that's going to be, the starting output value is 2,000 meters and the ending output value is 5,000 meters. What's one input variable that we could apply here that might make sense? What's that? Meters traveled, like, what do you mean meters traveled? Like, okay, so the distance okay, it could be that, sure. We could do that, right? That would work. We could say that total distance we've walked. That might be our input. That would work. Okay, so this would be distance walked along the trail. So it's like if I'm taking one of those little odometer wheels, those cross-country things, you know, where you measure out courses, and I'm just carrying that with me. Starts at 0, and it ends up at some value, right? Okay, if that were the case, then we'd probably start at, we'll just make that 0. That's what we were going to say. We started. That was our starting distance walked, and our altitude was 2,000. Okay, as we move along the trail, the distance walked is always increasing, isn't it? Agreed? Okay, so then there's going to be some point at the end of this thing where we've walked some distance of, I don't know, we're measuring this in, let's measure this in kilometers, and let's say we walked a total of 10 kilometers and we got up to 5,000, right? Okay, is this a continuous function? Okay, why, you're right, but what's your, prove it, what's your reasoning?
Because you're continuing to walk and you go higher, or no matter what, you're continuing to walk, even if you stop for a second to, like, water break, you're not moving, therefore
Okay.
you're not walking.
Okay.
So as you continue to walk, it doesn't matter if you go up or down, you're still walking.
Okay, good. So then, good. So what would be, let's look at this. Sometimes a logical attack to take on problems like this would be to say, what would make this thing not continuous?
Teleportation.
Okay, for it to be not continuous, what are the kinds of places where a function looks discontinuous, where it is discontinuous? If there's, we only had certain types of discontinuities.
Point.
Okay, we could have a hole. What would a hole mean? A hole, could a hole, I mean, like a hole doesn't really apply here, right? Because a hole would mean there's going to be some distance that's not defined somehow. I mean, there's a place you could step that where you would just teleport out of, I don't know. Right, okay, that doesn't happen though, right?
Wait, how does it?
Well, you can stand, there's no place where you couldn't stand on this trail and have some distance from the beginning, right? That's just, I mean, how do you prove it? Well, because that's the way existence works for us, right? It's never not happened that way. So that's one place, point discontinuity. What's another type of discontinuity we could have? A jump discontinuity. Think what that would mean. If there's a jump discontinuity, that would mean that you're walking along and then instantaneously I'm going to go from, 2,000 feet to 3,000 feet. That doesn't happen. Even if you're climbing something really steep, you're still having to move along. Your distance is still increasing, right? Everybody get that?
Yeah.
So you can't just spontaneously teleport from one place to a different place. That's what a jump discontinuity would require. And then the third kind would be an infinite discontinuity, which obviously you can't do, right? You can't ever have an infinite elevation, so that's also impossible. So we could say then that there is no way that, because any type of discontinuity is inconsistent with reality, we know this function has to be continuous, right? And so if it has to be continuous, even though our elevation might bob up and down as we travel along that trail, we know that at least one place we're going to have to pass through that elevation band, which of course we know that's the case, right? It has to be that way. What would be, so see if you can come up with another, because there's not one way to do this, but that way proves it right there. That's fine. What's another input variable we could maybe use? Time. Time would also work, right? We could have a stopwatch going, and if we start our stopwatch at time t equals 0, we're just going to move along. We might pause for a while, but if we pause for a while, that just means that our elevation just stays the same, right? But there are no gaps in time, and there are no gaps in elevation, so the function is still going to be continuous with time. Maybe it takes us to get there. Maybe it takes us, finally, we get there after, 4 hours. Well, somewhere in between time 0 and time 4 hours, we're going to have passed through that intermediate value. That's kind of cool that we can do that, isn't it? That's a rigorous proof. So we just proved that not only does it seem like you have to, we just mathematically showed by IVT that you have to. There's no alternative, right? You have to pass through that elevation zone at least once, that elevation band. Okay, give me thumbs on that. Okay? So there it is again. That's out of another textbook, but you've already seen it several times. It says the same thing. Okay, let's try this. Show that f of x equals x minus cosine x has at least one zero. Prove it. You can prove it using IVT. How? What's that? Okay, this one would require us to not use the unit circle because we need to have a function that's going to give us outputs as a function of an input. So you're thinking more along the line of like the graph of a trig function type of a thing.
Is k equal to 0?
So k equals 0, doesn't it? Right? Everybody agree? So we need to engineer this thing in such a way that we're going to guarantee that we're going to pass through the line y equals 0 at least once, right? Okay, so let's go back and look at our picture again. We're going to keep going back to this picture. So here's our picture. This time, the horizontal line, the value of k would have to be 0. Well, what would that mean about the rest of this then? What would that say about the values of f and a and f of b? What would they need to be? Okay, one has to be positive and one has to be negative, right? Because that would put 0 in between a negative and a positive value. And if we could just show that the function is continuous on some interval, right, between a place where the function has a negative value and a place where it has a positive value, that would guarantee that it's got at least one interior place where it's passing through 0. Okay, does everybody see that? Give me thumbs on that. Is that making sense? Okay, so we would draw our picture then like this. So we want this to be our value of k. So you guys got to help me find a value of a and b then. Okay, so if I pick -1, that's going to give me, we could maybe do that. Let's try that. Can you think of an easier one? -1 and 1 would work, but let's pick values that maybe we know on the unit circle. What's a -1 we could pick? An easy value of x that's going to give us a negative output. I mean, these are all reasonable suggestions, but just pick an easier one. Like, what's the easiest value of x you could pick that gives you a negative outcome? How about 0? Right? Right? Because 0 minus, what's cosine of 0? 1. 0 minus 1 is -1, right? Okay, so let's, I just want to pick one so my picture is going to look good for you guys when you look back at your notes. So we're going to pick 1 at 0. That's going to be my value of a, right? And that's going to give me, darn it, I keep. So at 0, we get a y value of 1. So the coordinates at this point are 0, -1. Agreed? Okay, what's a value that's going to give me a positive output? 1's tricky. Just pick one that we know is going to work. Well, okay, 2 has to work, yeah. 2 would work. I'm going to pick pi. Just because pi, what's cosine of pi? -1. Okay, so if I pick pi, if I go out here to pi, would you agree that f of pi just equals pi minus -1, so it's pi plus 1? Right? That's guaranteed to be positive, isn't it? So we go out here to pi. And is this function continuous on the closed interval from 0 to pi? This function. It is. Okay, it is, but now tell me why. Say it again. Okay, but we're not worried about any of that. We just want to know, do we meet the criteria, right? What are the criteria for IVT? We have to have a function that is continuous on a closed interval, and we have to have an interior value on that interval, right? So our interval is from 0 to pi. Look at this function, f of x equals x minus cosine x. I just want you to tell me why that definitely is continuous. It's continuous everywhere. There's nowhere where it's not continuous. How do I know that? Look at the pieces, right? Look at the pieces of that function. Is x continuous everywhere? Yeah. That's just y, that's a horizontal line, right? Is cosine x continuous everywhere? It's just a wave train forever, right? So if both of the terms in that function are continuous, well then how could you ever add or subtract them and get something that's discontinuous, right? Does that make sense? If all the parts, we'll just call it for now, if all the parts of a function are continuous, then the whole has to be continuous, right? Now, that would be a problem if we had a quotient. That wouldn't be true though, right? Then the zeros of the denominator would be places where it's discontinuous. But we're talking about we're adding up separate terms. If each of those individual terms is everywhere continuous, then the whole function has to be, doesn't it? Right? Would it work for a product of factors? If I've got two factors a product of two factors that builds a function, if each one of those factors is continuous everywhere, would the function have to be? Yeah, it would. Does that make sense? We have a danger, though, if we have a quotient, because then we introduce the possibility of dividing by 0, right? Okay? All right, so you get the idea. So this thing is continuous. Do we meet the criteria? Yes. F is continuous on the closed interval from 0 to pi. Check. Right? Is k an intermediate value? Yeah, right? Y equals 0 is between f of 0 and f of pi. Check. We met both of the two criteria, so IVT absolutely guarantees that this function has to pass through y equals 0 at least once between 0 and pi. Anybody see that? Okay, we know it has to. Where does it pass through? I don't know. We have to find out. Solve an equation to find out. Existence theorems don't give us answers. They just tell us if we should bother looking for an answer. If we know there's an answer there, and we do. Okay, give me thumbs on that. Does that make sense? Okay, ask some questions. If you like, help me clarify. If one of you has a question, more than one of you has a question. See if you can ask a question to help me clarify this for you.
How did we decide that y equals 0 was a 0 function?
Because of what the question was. What does it ask about? Good question. It says, show that this function has at least one 0. What's a 0 mean? That means it passes through y equals 0, the x-axis, right? So that needs to be our intermediate value. Okay, what else? Ask another question, somebody. Okay? All right, let's look at another one. Okay, when can you apply the intermediate value theorem? So how about this one? If f of x is continuous, you guys have to tell me yes or no. Give me thumbs up or down. If f of x is continuous on the closed interval 0 to 2, f of 0 is positive and f of 2 is positive. Can we use IVT to conclude that f of x has no zeros in the interval from 0 to 2? Okay, so the reasoning here is that this is not an application of IVT, right? Because it's saying that y equals 0, IVT is intermediate value theorem, right? IVT. So for f of x to have a 0, that would mean y equals 0. Well, the value of the function at the start and at the end, they're both positive. So 0 is not an intermediate value, right? So the theorem does not guarantee it does not guarantee a 0. An interior 0. You get what I mean by an interior 0? Well, what does the word interior mean? Between, right? Between 0 and 2. So interior means on. Okay, but I disagree. I sorry on your birthday to do this to you, but I disagree with you. That's not enough, right? Just because IVT does not guarantee, you got to hear this. You got to really focus on this statement to get this. Just because IVT does not guarantee an interior 0 does not mean that one doesn't exist. It just means it can't guarantee it. One certainly could still exist, right? We just haven't met the criteria of the function. Let's draw a picture where one does exist just to prove it, because all we need is one counterexample, right? So between 0 and 2, our function is positive valued at both places. So say there and there, right? So that's 0, f of 0. This is 2, I'm just making these up, 2, f of 2. Could you possibly draw a continuous function that still passes through the x-axis? Yeah. Here's one right here, right? I mean, it could happen. It's just that IVT can't guarantee that it happens because this is not an interior value. So it can't make that guarantee, but it certainly doesn't mean that it couldn't happen, right? Give me thumbs on that. You get it? Okay. So the answer is no, and there's our picture. Okay, ask questions if you need to on that one, right? Because again, the question is just saying, could you use IVT to include that it has no zeros on this interval? No, right? The absence of proof does not mean proof of absence in this case, if that makes sense, right? You get the idea? Okay. Okay, how about this one? Can we use well, let me go back. I feel like I don't want to rush. Give me thumbs on that, first of all. Give me thumbs. I'd be up, down, sideways. Be honest. I want to know where we are in this. Okay, if your thumb's not up, can you find a way to ask a question? Work hard. See if you can find a way to ask a question that possibly I could answer to help clarify things. Matthew, can you think of a question? As many as you want. Because if you've got them, other people do. Yeah. Okay, so now think. Say that one more time. One more time, say that again. Okay. Okay, the blue part. So let's read through this line by line, and let's just make sure we understand how this could apply, right? Let's look at a situation where it would apply first. So I got to have, you guys got to be, on this one though, this is such a sophisticated thing. We just got to be, raise your hand if you want to contribute something, but otherwise don't talk. We got to have massive train of thought here, super concentration. So let's pick an example where it would apply. How would I have to tweak this so it would apply? If this function is continuous and f of 0 is positive, and what if we said instead f of 2 were negative, then we could, that IVT would absolutely guarantee that between 0 and 2, the function would have to pass through 0, because it's going from a positive output value to a negative output. Is that y value being positive to y value being negative, right? That would guarantee that there is an interior value that is a 0, right? Okay, but it doesn't do that. It's positive at the beginning and positive at the end. So 0, y equals 0 is not an interior value, right? And so IVT has no business saying anything about what happens at y equals 0, because it doesn't meet any part of the criteria here, right? IVT can't guarantee that it passes through 0, because 0 is not between the value of the function at x equals 0 and the value of the function at x equals 2, right? So it does not apply. But here's the rub. This is the part that people have trouble with. Just because it doesn't apply does not mean that it couldn't happen. We just can't guarantee it, right? It simply doesn't apply. Like an interior value, some value up here, we could guarantee that it has to pass through that value of y, because that's in between the two endpoints, right? But y equals 0 is not between the two endpoints. So IVT can't say anything about it. It can't say that it guarantees that it does or doesn't pass through there. And here's an example of a function that does pass through y equals 0. Here's a different function. A different color. Here's a different function. The orange one is a function that does not pass through y equals 0. They both, neither, IVT really can't distinguish between those two, because it has nothing to do with either one of them, because this is not an interior value. Does that make sense? Okay. So it really does not apply here. If we don't meet the criteria of IVT, it can't say anything, it doesn't tell us anything useful at all. Okay? Does that help? Okay. Give me thumbs now. I want to see where we are. So that helped? Did that really help? Be honest. Did that help? Because we were sideways before. Did that help? Okay. All right. All right. Okay, try this one. Try this one. It just takes a lot of thinking about this. So first of all, my question is just, we're not even going to do it, but just can we use IVT to prove that the function f of x equals 1 over x has a 0 on the closed interval from -1 to 1?
No, this function is not.
There you go. You can't. Because what are the two criteria? It has to be continuous on the closed interval from -1 to 1. And where is this function discontinuous? At 0, which is on that interval. So no, right away we can see that it's not going to apply. Okay, is the function continuous? No, we failed that one. Now it actually passes the second part, but we don't even care, right? 0 is an intermediate value, because the value of the function, I'll just show this to you. It's irrelevant, but f of -1 is -1, right? F of +1 is 1. So 0 is an intermediate value, but who cares? Because we failed the first criterion, so it doesn't apply. Okay? Make sense?
I have a question.
Yes.
If the function is not continuous, but it is continuous over the interval.
That's fine. It only has to be continuous on the closed interval. Yeah, doesn't make any difference. Outside of that, IVT doesn't care. It only cares about the part in between the endpoints, right? Okay, how about this one? First of all, do we meet the requirements? Is IVT continuous on this interval?
Yeah, because 0 is +2.
Yeah, where's the only place where it's discontinuous? At 2. Is 2 inside or outside that interval? Okay, we're good, right? So it actually, even though this is a discontinuous function someplace, it's continuous on the interval that we're inspecting, right? So we're good. What about the second part? Is 18 an interior value? Well, we just have to plug in, evaluate the function at 5/2 and evaluate the function at 4 and just see. F of 5/2 is 55 over 2, which is bigger than 18. f of 4 is 14, which is less than 18. So 18 is between f of A and f of B, right? So give me thumbs on this. Does IVT guarantee an interior place where the function equals 18? Yes, it does, right? Okay, how do we find that? We just have to do algebra and solve the equation, right? To solve it, we would just go set, how would we solve it? I mean, it's super easy. What would we do? Yeah, set f of x equal to 18 and solve the equation. That's it, right? Okay. All right. Okay, this is a great one to close on. Think about this one now. This is pretty cool that you can, and I'll tell you what, you can do this. So at 8 a.m. on Saturday, a man begins running up the side of a mountain to his weekend campsite. There's the picture, okay? On Sunday morning at 8 a.m., he starts right at 8 a.m., he runs back down the mountain to get back to his car. It takes him 20 minutes to run up, but only 10 minutes to run down. At some point on the way down, he realizes, I don't know how you would realize this, but he realizes that he passed the exact same place at exactly the same time of day. Would that happen? It has to. Does it seem like that's a coincidence that you would happen to pass by the same place at the same time? Because it's not. You can prove that it has to happen. It has to happen. Now think about how you're going to do this over the weekend, because we'll come back and talk about this on Monday, right? So take a picture of this. Everybody take a picture with your phones. Take a picture. There, take a picture that you can read and see. Okay, I'll do that. Yeah, okay, I'll do that. So think about the way you're going to have to do this, right? You're going to, in order to use IVT to prove this, you're going to have to come up with some continuous function, right, that relates to the guy's position on the mountain as a function of time, right? And you're going to have to somehow show that there's an interior value that would correspond to him passing by the same location at the same time of day, and then just prove that that happens. This is a really cool problem. So try that. Try that.